Alrighty. Wasabi, you guys. Welcome to the 4th lecture of linear algebra for computer science majors. In this lecture, we will be learning about determinants. Now, what is a determinant? Let me show you. Let me first write out we'll first start off with a 2x2 matrix. So for any 2x2 matrix, okay? For any 2x2 matrix, we write as det. This is our determinant of A. Okay? And the way this is equal, the formula, is equal to AD minus BC. Okay. Now, does that look familiar to you? Right? This formula right here, just this portion here, what does this look like? What does this remind you of? If you remember our last lecture, this was part of the formula for the inverse of the 2x2 matrix. So let me actually rewrite this. The inverse of A, or for any 2x2 matrix, is equal to AD minus BC, right? And if you remember, it was D negative B negative CA. Right? So that was our inverse formula for any 2x2 matrix. Let me actually double check. Yes. Okay. So we call this portion the determinant of A. Now, why do we call it the determinant of A? It's because this is what determines whether A, this matrix, is invertible or not invertible, right? That's why we call this the determinant of A. It determines whether A is invertible, okay? And it's true, it does determine whether it's invertible or not. If you remember our last lecture, if this equals to 0, then the matrix does not have an inverse. It is not invertible because you cannot divide a number by 0. So if it's not 0, then congrats, you have an inverse, okay? So that's pretty much it. That is what we call the determinant, right? If this is equal to 0, it's not invertible, okay? If it does not equal to 0, then it is invertible. You have an inverse matrix. Congrats, it's like, wow, it's a miracle. You have a baby. If it's not invertible, maybe using childbirth was probably not a good analogy, but you get the idea, right? If it's invertible or not invertible, this helps us determine quickly if the matrix is invertible or not. All right, cool. So now let's do an example. So now we have a 2x2 matrix B. Okay, is B invertible? Well, to easily see that, we must determine the determinant of B. The question is, to answer if this matrix is invertible, if B is invertible, we just have to make sure that determinant of B does not equal to 0. So here we see that determinant of B is, I guess I'll write it horizontally. The determinant of B, we have AD, which is 1 times negative 1, that's negative 1, minus 4 times 3, that's 12. So the determinant of B is equal to negative 13. Awesome! It's not equal to 0. So what that means is that because this is not 0, it is invertible, right? Congrats. This matrix has an inverse. So that's it, right? So we just compute the determinant. Computing the determinant helps us check if the matrix is invertible or not, and it's very quick and simple, right? So absolutely amazing. Okay, now now that we found the determinant of B, the next question is, what is its inverse? How do we find the inverse of this matrix, right? If you remember the formula, right, the inverse of B, it's simply just the determinant, 1 over the determinant, which is 1 over negative 13, and then you just kind of switch places here, negative 1, 1, negative 3, negative 4, and you're done. That's pretty much it. Okay? Simple as that. Also, you could put like multiply the scalar if you want. Your professor's probably gonna make you do that, but in this case, it's not really. I mean, I just don't like fractions. I just don't like. I'm not a fan of fractions. But anyhow, it's that simple, right? Very simple, easy process. Okay, cool. All right, now before we jump the gun to more determinants, let's learn probably another concept that we must learn first before we get to some higher level determinant stuff. Now, we have a 3x3 matrix here, okay? And let's say we have like a very humongous matrix, and like the majority of the entries are like zeros, but then for some reason there's this one area that has a bunch of numbers, while the rest of the areas of the big matrix is a bunch of zeros and stuff. I'm very lazy, so I only wrote it in 3x3 matrix form. So let's say here in this area, we're interested in the area that has the most non-zero numbers, right? In that case, it's this portion here. If my big head can move out of the way, it's this portion here, right? So if we're only interested in this part, then what we can do is we can create what we say, oh, if I can stop lagging. Oh god. Whoa. Okay. So what we can do is we can create what's called a submatrix. Okay, a submatrix. Yes. So now, let's say if we're only interested in this portion here, we can create a submatrix. Okay, and so the way we write it is we write A11. So it's kind of like entry, but it's capitalized, and so it's A11. Then now, so 1, these numbers represents the row that you want to delete, and the column, the row that you want to delete, which is this way. The row that you want to delete, and then the column that you want to delete, which is also here. Okay? So that's what these two numbers represent. So it's the row and the column that you want to delete. In this case, we want to delete this and this, so that we only focus on this submatrix here. And so our submatrix for A11 is 1, 2, and 2, 4. Okay? So if you have a very big matrix and there's only an area that you only want to focus on, then you can create a submatrix. You can program, you could take the code, or just kind of like if you're given a very nasty big matrix, you could just only focus on area. You could just create a submatrix instead, and then put in whatever you want to do, whatever. But yeah, so it's called a submatrix. So we can do what's called a submatrix. Okay, and we write it like this, where the numbers represent the rows and the columns that we want to delete. Okay, so it's a very important concept that we understand what is a submatrix. And so now that we know what a submatrix is, it would be easier for you to understand how determinants work for bigger, nastier matrices. So now let's do an example of a 4x4 matrix here. We have M equals this big minesweeper looking matrix here. And we have two questions. right? What 3x3 submatrix has the most zeros? If you just, I mean, it's easy to see that if we look at a 3x3, if we choose any choose any 3x3 submatrix from this 4x4 matrix, right? We can easily see that this portion here has the most zeros, right? Out of the other areas, because we have this 0 zigzag here, and there's like 5 zeros. The rest, let's see, here there's 4 zeros here, and there's 2 zeros here. This portion here, this 3x3 portion here has like 5 zeros. So this would be our 3x3 submatrix with the most zeros. Okay, but how do we write it? So the way we write our answer is we write it as capital M, and then the row and the column that you want to delete. Okay, so that means that we want to delete row 4, we want to delete column 4. So our answer will be M40 or M44. Okay, this is our submatrix with the most zeros. In this case, it would be 1, 0, 0, 0, 0, 0, and then, oh, I lied, it has 6 zeros. Would you look at that? 6 zeros. That is a lot of zeros. Okay, so that's our submatrix for the most zeros. Now, what about the least zeros? Which portion has the least amount of zeros? Right. Of course, you can already see that it's this side here, right? This portion of the 3x3 has the least amount of zeros. We have a lot of non-zeros here, right? 1s, 2s, 5s, and 7s. So, how do we write that? How do we write our answer? And again, we write it with a capital M, and we delete the row and column that we want, right? In that case, we want to delete the first row and the first column. So that means that our answer would be M11. Okay? In which our submatrix would look like this. It will be 0, 1, 2, 1, 2, 0, 5, 5, 7. Okay? And that will be our answers. And notice that all of our matrices here, right? M there, M44 and M11, they are, if you remember, these are symmetrical matrices, right? These are, if you have a symmetrical matrix and you take a symmetrical submatrix, or if you take a submatrix with like a repeating row and column like this, then of course your submatrices will also be symmetrical as well. Awesome. So now you understand how submatrices works and why we use submatrix. Okay. Now you're probably thinking, so but what about big matrices with determinants, right? How do we deal with finding determinants for bigger matrices? How do you compute a determinant for like a 3x3, 4x4, or a 10x10 matrix, or something ugly, whatever, right? So here's the thing, okay? It's not like a 2x2 matrix where it's like, oh, it's like, here you go, a formula. You see, for bigger matrices, shit is nasty, okay? It is disgusting. Oh, and I'm lagging. Oh god. Whoa. Okay, I'm back. So, yeah, you see, for bigger matrices, shit is nasty, okay? Shit is very nasty when it comes to a bigger matrices and computing the determinant, okay? Now, let me just show you something. Just let me show you something real quick, okay? I'm gonna show you back to the 2x2 matrix, okay? Just consider this any 2x2 matrix, right? Remember that, the determinant of A, we know what this is, right? This is equal to AD minus BC. Okay. Well, you see, I just straight up gave you the formula because it's simple, right? But here's the truth. The truth is the determinant looks like this because we have A. Now, D, what is D? D is here, right? What if I told you we're going to make a submatrix out of a 2x2? Now, I know, I already told you, like, it's useless to have a 1x1 matrix, but just bear with me here, okay? D is, we're going to make D the lonely submatrix, okay, which means that we have to delete column 1 and row 1. So row 1, column 1, so we will have A here, and we will have the determinant of A 1, 1. Okay, that's what D is. Now, what about here? Minus BC. So minus BC, we have B times, and then what is C? C is the submatrix of what? Of row 1, column 2. So C is a submatrix. So C is equal to the determinant of A, where we have to delete row 1 and column 2. Okay? So the truth is, this is actually how it, this is where it came from, right? This is where the formula came from. This is where the determinant came from. It's because of submatrices, right? To compute the determinant, we used submatrices to find the determinant, okay? In this case, we have A11, and then we have A12, and there's a minus here, okay? Now you're probably thinking, okay, so what? What does this have to do with bigger matrices? That's the thing. For bigger matrices, it's not going to look like this. It's going to look like this. It's going to look like that. This whole portion here. This is what the determinant would look like. When you compute the determinant, it's going to look like this for bigger matrices. And you can already imagine what it would look like for bigger matrices. This is just a 2x2. Imagine a bigger matrix. Okay, now don't freak out. Don't freak out. Again, this is a Comp-Sci major course. So again, we'll be using a calculator, but I'm just showing you how this is computed. Okay? Alright, cool. So now let's go ahead. Now that we understand that we can express our determinant formula in terms of submatrices, we're going to apply the same thing for bigger matrices. Okay? So, what would it look like for a bigger matrices? Yes, unfortunately, we cannot write it like this. We're going to have to write it like this. Okay? Oh boy. Alright. So for any n by n matrix A, where n is equal or greater than 3, so like a 3x3 matrix or a bigger matrix, right? Here's what the determinant of A would look like. The determinant of A, are y'all ready for this? Oh boy. The determinant of A is going to equal to the entry A11 multiplied by the determinant of a submatrix A11, and then we subtract it with A12 times the determinant of the submatrix A12, and then we do plus entry A13 times the determinant of the submatrix A13 minus A14 times the determinant of A14. Okay, entry submatrix plus, and then it keeps going, and it keeps going, it keeps going, and we end up, whatever n is, you should get something like this. At the end, n plus 1 of whatever entry A1n of the determinant of a submatrix A1n. Okay? I know it's a very, very long-ass formula. Okay, I know. This is nasty. But again, I'm not gonna give you anything bigger than 4x4 matrices. Or maybe a 5x5 matrices, but mostly a 4x4 or less. Most commonly, I'll only give you like a 3x3. Okay, but yes, unfortunately, this is what the determinant of a bigger matrix would look like. Okay, now, however, I know you're not going to memorize this. You're not going to memorize this. I'm only showing you a skeleton of how we compute determinants, or how we, input a code or program a determinant calculator. So, okay. So this is how we compute a determinant for bigger matrices, right? But to save our to prevent us from having carpal tunnel, from inputting all this into the code, we can simplify this a lot more. Yes, we can simplify this a lot more, and let me show you how. Okay? So we can simplify this further. Let me actually write this in yellow. Okay? We can simplify this a lot further. I want you to consider C. Okay? Consider a capital letter C. It's not lowercase, it's capitalized. Capital C. And then we write mn for the matrix size, right? M for row, n for column. And now the formula that we write for this is -1 with m plus n, and then the determinant of A mn. Okay? So just consider that. Okay? Just consider this. Okay? And now our determinant looks like this. Then the determinant of A is equal, and then this is how we write it. We write our entry. We go ahead and write our entry. Oh god, if I can stop lagging. It's actually capitalized. Okay? So now we have a simplified form. Oh, thank goodness. Right? Thank freaking goodness. We have a much nicer looking formula for the determinant of a big matrix. Of course, it is a lot more work since we do have to, we still have this to deal with, right? Okay, so nice. So we have a simplified form of determinant. Now it's easier for us to memorize what the formula is. The only difference we have to focus on is just this portion here. What is CMN? Okay, so cool. So the reason why I want to use CMN is because CMN, this here, CMN is the cofactor. Okay, so we call this the cofactor. The cofactor. Okay, we call it the cofactor of A, of matrix A. Okay, so this is how we get our formula. This is how we come up with finding determinants for a big, gigantic matrices. Okay, so of course we turn it into submatrices, right? But of course it was a little nasty, and so we simplify it further by considering what we say the cofactor of A, right? So this is the cofactor of A. This portion here is the cofactor of A with the negative, right? So we have the cofactor of A, and now our determinant is a lot nicer. So, to prevent us from having carpal tunnel, right, instead of computing our code like this, we can, consider a cofactor variable here, and then just plug in, and this is how we just compute the determinant like this, so that it's just a lot more clean and nicer. Okay, so this is how we compute. Like a gigantic square matrices, right? Computing big matrices using cofactors. All right, I know it's still a little nasty, but just bear with me. It'll be a lot. It won't be as bad. It won't be as bad, but it does get annoying. I will say, especially computing this by hand. Okay, so now let's do an example, right? Let's say you're given, a professor gives you this problem, compute this, and you're looking at this like, what the hell is this, right? It looks like a matrix, but then those aren't brackets. They're just like absolute value looking lines, right? This is a different way of saying compute the determinant of this matrices. So if you see like just a straight line between a huge matrix, this is how we write the determinant, right? Compute the determinant of this 3x3 matrix in this example. Okay, so let me first turn this into a 3x3 matrix, right? Just to give my to prevent myself from losing insanity when solving this determinant. Now, 1, 1, 2, we have 1, 2, 3. Okay, and we remember our determinant, right? What's the easiest way to remember our determinant formula? It's DET. Okay, DETA is equal to, and then it's just A11. Oops, I'm sorry. A11 C11 plus A12 C12 plus A13 C13. Okay? This is just to help us memorize the determinant. Okay? Now, what this would equal. Alright. So we have A11. What entry is that? That is 2. Okay. So that entry is 2. So we have 2 and then times what? Okay. So C11, what submatrix is that? So this means that, our cofactor for C11 means that we're dealing with a submatrix with A11, right? Now, of course, we have the -1, 1 plus 1. So that's going to be positive. And then we have to compute the determinant of what submatrix? A11. So that means we're deleting row 1, column 1. So we're computing the determinant of submatrix A11, which is 1, 2, 2, 3. Okay? And then we continue over here. A12 plus A12. What entry is that? A12. A12. So that's 1. Okay. And then -1 of 1 plus 2. Now we're computing the cofactor, which is -1 to the power of 3. That's going to be a negative. Computing the determinant of a submatrix of A12. So deleting row 1, column 2. So we have -1, 2, -1, 2, and then 1, 3, right? Because submatrix A12 means deleting row 1, deleting column 2. Okay? And we get this submatrix. Next, we have plus A13. What entry is A13? That's also here. A13 is equal to 1. Okay? We know this is positive because -1 to the power of 4 is positive. So I'm just going to skip that. Our determinant is computing the determinant of submatrix A13. A13, delete this, and delete the third column. Okay, so our submatrix is here. So we have to compute the determinant of -1 of 1, 1, 2. Okay. Oh boy. I know. Okay. So, so this is positive. Let me just kind of crouch on my knee. Let me just get on my knees. So here we have 2 AD minus BC. That's -1 minus AD -3 minus 2. -3 minus 2. That'll be like -5. Oh wow. Okay. Plus 1 and then AD minus BC, that's -2 minus 1. That's -3. Okay. I believe I did this correctly. But yeah, we should get 2 -1. Yeah, that seems about right. And would you look at that? Wow, let me double check if I'm seeing this correctly, because I'm getting 0. Yeah, this determinant. So the determinant of A. Whoa, if I can stop lagging. Okay. Yeah, alright, I'm no longer lagging. So this is surprisingly interesting. The determinant of A for this 3x3 matrix is equal to 0. So what does that mean? Because the determinant is equal to 0, this matrix does not have an inverse. It is not invertible. Okay? It is not invertible. Because the determinant is equal to 0, this big matrix does not have an inverse. It does not exist. Okay? Cool. So that's the process of computing a determinant by hand, right? But you don't have to do that. You can just use a calculator, or practice using Python or C++, MATLAB, and create your own determinant calculator. Okay, I'm just showing you the process of how it works, the method of computing it. Okay, cool. Awesome. So now that we learned how to compute matrices, either 2x2 or big, gigantic matrices, I'm going to show you a special type of matrix now. Kind of like how we learned symmetrical matrices, zero matrices, identity matrices. We have another type of special matrices that we can have. Okay? We call them triangular matrices. Now you're probably thinking I'm like psychotic for thinking of triangular matrices. Okay? No, it's not what it looks like. It's not what it looks like. It's not what you think it is. It's not one of these you know, this thing, right? You're not gonna, no, this does not exist. This isn't what I meant by triangular matrices. You're not gonna have, you know, this, or I'm sorry, that's backwards for you guys. But something like this, I cannot draw backward too. There you go. Right? No, you're not. This, dear God, no. we're not gonna deal with actual triangular matrices. This is not what I meant when I say triangular matrices. So do not freak out. Although that would be a little cool, but also at the same time, very, very horrifying. But triangular matrices. So what do I mean by triangular matrices? What on earth is this? Who on earth says triangular with matrices when all matrices are squares, right? So a triangular matrices, I think it's better if I just show you what the matrix looks like rather than tell it to you in words. But in general, pretty much it's just a square matrix where half of, well, I wouldn't say exactly half of the matrices, but I would say like about like a triangular portion of it are zeros. It's hard to explain in words. It's better if I just show you. In this case, we have this example here. I'm just gonna put a 0 there just to help you understand. Okay. Notice that we have a triangle section of zeros. Okay. This is what I mean by a triangular matrices. Okay. Look at this portion here. We have a triangle amount of zeros. Okay. That looks awful in your camera perspective. It would be like, is that better? That looks so much nicer. Okay, so we have this amazing triangular portion of zeros. Okay, this is what we mean by a triangular matrices, and it doesn't have to be at the bottom. It could be at the top too, right? It doesn't have to be a bottom. It could be a top. So, oh my God, fucking hell! I cannot believe I said that. 2, 0, 0, 0, 1, 3, 0, 0, 6, 8, 4, 0, 7, 9, 0. I'm just gonna put a 0 there. It's just for the random, just to make it more realistic, so that you don't freak out. But it could be literally any whatever numbers exist. It doesn't have to be non-zero. It could literally be anything, as long as we have a triangular portion of zeros here. Okay, so this is what we mean by a triangular matrix. In fact, it doesn't even have to be like this direction. It could be the other direction too, right? We can also have like another, a bunch of zeros on top. Like it could be this direction as well. Right, 1. I'm very lazy, so I'm just gonna write this. Right, is symmetrical triangular matrix. So right, so all of this is a triangular matrix. Okay, they're all triangular matrices. So that's when we have just a bunch of zeros, a triangular shape of zeros inside a square matrix. This is what we call a triangular matrix. Okay, now we do name them. We do have a name for them. Okay, if the matrix have zeros at the bottom, okay, we call this an upper triangular matrix. Okay, so we call this an upper triangular matrix. Okay? And we call it upper triangular because we're focusing on this portion here, right? It's not like what I say where like it's shaped as a triangle, like an actual triangle matrix. No. It's just the entries, the entry shape of a bunch of numbers is the shape of triangles. In this case, this is an upper triangle matrix because a lot of the non-zero or any number stuff is at the upper corners of the matrix. Okay? Matrices here, where a lot of the any numbers or non-zero numbers that are at the bottom, okay, we call them a lower triangular matrix. Okay? Ooh, so this is a lower triangular matrices. These are lower triangular matrices. Okay? So again, right, lower triangular matrices because all of our entries are at the lower portion of, they're at the lower corner of our matrix. Okay? So this is our two types of triangular matrices. Okay? Cool. Now, you'd be very surprised how many times we will have a triangular matrix in, real world situations, right? Especially like Minesweeper, you will come across a lot of triangular matrices. So, and thank goodness for that, because I'm going to give you a formula for the determinant of A for a triangular matrix A. I am lagging like hell. Okay. So, for any triangular matrix A, the determinant of A is so much nicer. Thank goodness. So much nicer. Okay? And I just want to just let you know this is an n by n square matrix. Okay? So the determinant of A is equal to the entry 1, 1, entry 1, 2, and then so on. Oh, I'm sorry. No, I lied. I lied. Okay? So the determinant of any triangular matrix, the determinant is multiplying the diagonal entries, right? Oh, thank heavens. Right? You don't have to find the cofactors of each term. No. The determinant, we can just compute the diagonal entries, right? If for those who don't remember what these entries look like, right? They look like this. For any square matrix, okay? For any square matrix, they look like this. A1, 1 is here, A2, 2 is here, and then going down diagonally, this is A and N. Okay. So these entries here, these entries are the diagonal entries of a square matrix. Okay. So the determinant of A for a triangular matrix, for any triangular matrix, the determinant is just the product, just multiplying the diagonal entries. Okay, thank goodness. And you come across this a lot. You come across triangular matrices a lot in real life situations, especially in like Comp-Sci fields. You'll deal with triangular matrices a lot when given big, very big matrices. Okay, cool. Alrighty, so now let's do an example. So how do we compute the determinant of A? Right, it's very easy. It's super easy, right? Because notice that we have a triangular matrix. This is a triangular matrix because we have a triangle zero field here. And so because of that, our determinant of A is equal to just multiplying the diagonal entries. Okay, so we have 2 times -4 times -2 times 1. I mean, you can, if you want, you can simply just write it down, I guess. 2 times -4, -2, and then 1 is just, 1 is just 1. So here, this is what we have. So our determinant of A is equal to 16. Okay? And that's it. It's amazing. Thank goodness, right? Thank God for triangular matrices. This is it. That's how we compute the determinant for a triangular matrix. Okay? Cool. Now let me give you a real life situation problem. Do you remember what this notation means? Right? Compute the determinant of a 4x4 matrix. Okay, cool. Unfortunately, it is not a triangular matrix because this is not a 0, that's a 1. And so because of that, you may feel a little sadness inside. Okay? But don't worry. Okay? We have a lot of zeros. That's a good thing. That is a very, very good thing. And let me show you why. Okay? So when we compute the determinant, okay, I'm just going to call this DETA, because that's technically what this is. Okay? So when I showed you the formula of the determinant of A, I only used row 1, right? Because I always used A1, A2, A12, A13, A14, and so on. So I've been sticking with row 1. The truth is, you can actually use any row you desire. Okay? So you can choose, whether row 2, row 3, row 4. Let's say you chose row 4 instead. And so the formula would be like A41, A42, A43, A44, and so on. Okay? That means that you're using row 4 rather than row 1 that I showed you. Okay? So, okay, so we don't have to use row 1. Wait, so then, but now you're probably thinking, what's the point? What is the point of, like, why are we free to use any rows we want? Let me show you. Okay? Now, with the formula that I've been giving you, you're probably only using row 1, right? However, we can use row 2, right? Because when you're using row 1, right, here's what row 1 looks like. Let me just label this row 1. Okay. Using row 1. Okay. When you're using row 1, your determinant looks like this. The determinant of A is equal to A11, C11 plus A12, C12 plus A13, C13, and then A14, C14. Right? Now, what is our entry for A11? 2. So we have 2 C11. Okay. What is our entry for A12? A12, that's row 1. column 2, oh, that's a 0. So if this entry is 0 and we're multiplying 0, that's just 0, okay? A13, A13, again, A13, that's still affiliated with row 1, but now it's column 3. That's also a 0. So if that's 0, when we multiply that, that's 0. Okay. How about A14? A14 is here. Okay, so that's a 1. So that means that we have C14. Okay, so our determinant of A is equal to 2 times the cofactor of submatrix A11 plus the cofactor at 14. Okay? So it's 2 times the cofactor of 11 plus the cofactor of 14. Okay. So that's our determinant of A, right? So that's what it looks like when we use row 1. Now let me show you row 2. Oh, I am lagging. Oh no. Okay. I think I'm good now. Hopefully I'm not lagging. Still lagging? Okay, I think I'm good now. Alright. Now, let me show you row 2. The reason why I'm choosing row 2 is, what do you notice? Why am I favoring row 2? Well, you notice that a lot of zeros are canceling out, right? So less work for me. Now you understand why I chose row 2. Because at row 2, we have a lot of zeros! We have a lot of zeros. And so, at row 2, right, when we work with row 2, our determinant of A is equal to A, and then we say 2, 1 plus A22 C22 plus A23 C23 plus A24 C24. Okay? And now what do you notice? Well, the rest is 0 except 1 here. And this entry here, this here, is A22. So our answer, the determinant of A, is equal to 1 times the cofactor of 2, 2. And we're done. That's it, right? This is 0, this is 0, and this is 0. The rest is 0 except for here, right? This is equal to 1. This entry is equal to 1, right? Which is what we have here. And so the determinant of A, instead of computing this, where we have 2 times cofactor of 1, 1 plus cofactor of 1, 4, we have cofactor. Oh no, I'm lagging. We have cofactor of 2, 2 instead. That's it. Okay, so our determinant of A is just the cofactor of 2, 2. Cool. So that means now I can go ahead and write my solution. Thank you very much for this row, for giving me a lot of zeros, because now I can easily compute my determinant of A here. Cofactor of C22 is negative 1, 2 plus 2, and then the determinant of the submatrix A22. That means we are deleting this here, and we are deleting this here, right? We're deleting row 2, column 2. So our determinant is 201. We're deleting row 2, deleting column 2. So 020, 201, 020, and then 003. Okay, that's a positive number. So that's this portion is that's positive 1. And then how do we compute the determinant of this? Oh my god! The submatrix. of A22. Do you know what this is? This is a triangular matrices. This is a triangular matrix. This is a triangular matrix. Oh my goodness, look at that. A triangular matrix. This is such an easy determinant to compute, right? This is now equal, again, that's a positive 1, right? Because negative 1 to the power of 4, that's positive 1. So we have a positive determinant here. This is equal to 2 times 3. Our determinant is equal to 12. Awesome! And this matrix, this 4x4 matrix, does indeed have a inverse. So, I know I'm out of bound. I'll go behind my own drawing here. Okay, so the determinant of A is equal to 12, which is a very nice number, thank goodness. And it's all thanks to that row, the second row of our 4x4 matrix. Okay, and what a beauty, that fact that our submatrix turns out to be a triangular matrices. So that's even less work. Bing bada boom, we have our determinant nicely done. Okay, so that's how we nicely compute. That's how we take advantage of like rows and triangular matrices. Okay, try to find a row with the most zeros. If you end up with a matrix with no zeros, I am so sorry for you. You're just gonna have to just compute it with a calculator. Okay, hoping that your professor doesn't make you do it by hand. But here, thank goodness, we have a lot of zeros, so we have a more chance of having a triangular matrix. Okay? Thank goodness. Now that we understand how to compute determinants the efficient way, taking advantage of zeros, I just kind of want to let you know first, to find an inverse of a matrix, I just want to recap this. If you want to find an inverse, the actual inverse of a big matrices, you use the double augmented matrix. If you remember, right? We use the determinant to compute the determinant of a big matrix just to identify if the matrix has an inverse, right? And if it does, if a big matrix is invertible, right? If a big matrix does have an inverse, then you compute the inverse using the double augmented matrix that I showed you in lecture 3. Okay? So, just to recall again, we're not using determinants to actually compute, it's not like the 2x2 matrix formula where it's like, oh, okay, so the inverse of a 3x3 matrix is like 1 over determinant, and then it's not like that. Okay. I mean, you could possibly make a formula, but it would be, I can imagine how nasty it would be. So, computing determinants for bigger matrices just helps us identify if it's even worth computing the inverse for. That's all that determinant is, right? It determines if the matrix has an inverse or not. That's why it's called a determinant. Okay? So, again, computing the determinant of a big matrix just lets you know that it is invertible or not invertible. It just lets you know if it does have an inverse. And if it does, and you want to find the inverse of that big matrix, then you can go ahead and, compute with the double augmented matrix, right? If you compute the determinant and it says equal to 0, then it is not worth doing the double augmented matrix computing the inverse, because it will not have an inverse, right? Because the determinant is 0. So, just want to let you know that why we have to compute determinants for big matrices. Okay? Because, it's ugly, right? Using a double augmented matrix to find the inverse of a big matrix, and we realize, oh, there is no inverse, right? You just wasted time. So, that is why we use determinants for big matrices. Okay? Alright, so now that we learn determinants, we're going to go ahead and learn some properties with determinants. Property number 1 is that when to compute the determinant of a matrix where we have a scalar times a matrix, okay, then this is equal to c to the power of n times the determinant of A. Okay, so that's our first property. Our second property here is that the determinant of a transpose matrix, okay? So the determinant of a transpose of A is the same thing as the determinant of A, okay? It doesn't have to be a 2 by 2, it could be literally for any n by n matrix. This is true. The determinant of the transpose of A is equal to the determinant of A itself. Okay? Number 3. Okay. If two rows slash columns of A are equal, then the determinant is equal to 0. Okay? So if you have two rows or two columns of A that are equal, the determinant of A is going to equal to 0. Okay, let me show you what I mean by that. Here's what I mean by that. Okay? Or let me actually write it in absolute form, right? Let's just say like here. Okay? We have two rows that are the same, right? The determinant of this matrix is equal to 0. Okay, that's it. Right? Simple, right? It's equal to 0 because we have two rows that are the same, right? And the reason is because think of it like this, right? We have a 3 by 3 matrix, and then you compute the RREF. If you compute the RREF of this, then you're going to end up with a free variable. Now, the reason why I'm bringing this up is now imagine if you want to find the inverse of this matrix, you create a double augmented matrix, right? But you know that when you try to turn this into an identity matrix, you can't because there's two of the same rows. So it will not turn out as an identity matrix. It'll turn out something else, and it'll have a free variable, which is why, because of that, because it won't turn into identity matrix, that means that this matrix does not have an inverse. And if a matrix does not have an inverse, then the determinant of that matrix is going to equal to 0. Okay? So that's kind of how to picture it is, if you try to take the REF of this, it does not turn into an identity matrix because you can simply subtract this row to this row, right? And you just get, 3 zeros. Wait a minute, that's not an identity matrix. And, you get free variables, and now that means that when you put it in a double augmented matrix, it does not have an inverse. So, because it does not have an inverse, the determinant is equal to 0. Okay? So, to save some work, if you have two of the same rows, it's equal to 0. Okay? Same goes with two columns as well, right? 1, 2, 3, 1, 2, 3, and then you have like some random whatever, right? Two of the same columns, your determinant is going to equal to 0. Okay? And the reason here this also works is because here, right, the transpose of a matrix is equal to, the matrix itself. So if I transpose this, what happens? instead of having 2 of the columns that are the same, you get 2 rows that are the same. And when you have 2 rows that are the same, it equals to 0. Okay? So thank goodness for this property here. Okay? So, if 2 rows and slash columns of A are equal, the determinant of A is also equal to 0. Is equal to 0. Okay. Number 4. Now, if one row slash column is a multiple of another, the determinant is equal to 0. Okay. Alright, so if you have one row or column that is a multiple of another, the determinant is also equal to 0, right? It's literally kind of like the same thing here, except you're, oh, well, let me just multiply this by like 2, right? Well, guess what? According to if you remember our 3 legal actions, you can literally just take away this. I'm sorry, not take away. Factor out this, right? Oh, okay. Divide this row by 2, and now you end up with 114. Oh, now you have the same, 2 rows that's equal to 0, right? That's literally like this. Again, right? So 3 and 4, they're technically the same thing. It's just that with 4, it's just letting you know, your 3 legal action says that you can just factor out a multiple. Okay? Okay. Cool. So, that's our 4th property. Now, there's 2 more. I have to kind of go in the ground a little bit. Alright, so property 5. For 2 square matrices A and B, okay, the determinant of AB is equal to the determinant of A and the determinant of B. Okay, just to save you some time. For n by n matrix B. Okay, so whenever you need to compute the determinant of AB, this is equal to the determinant of A times the determinant of B. Okay, so you can technically factor it out like this. Okay, so this means that, in number theory terms, we say that the function determinant is multiplicative, but we won't use that word. This is linear algebra. This just means like the determinant, you can just separate it pretty much. Okay? All right, but remember, AB has to be defined, and obviously AB are both square matrices. Okay? Now, our last one for number 6. Okay? For number 6, let's say that if A is invertible, then the determinant of inverse of A is equal to 1 over the determinant of A. Okay, so here are our 6 properties. There we go. Okay, So we have property 1, where we have the scalar multiplication. Okay, then that scalar will be powered by n. We have that the transpose of a matrix is equal to the matrix here, right? The determinant will be the same. All right, if 2 rows or 2 columns of A are equal, the determinant is equal to 0 because, if you remember how our double augmented matrix works, it needs to be, one side has to become an identity matrix. But of course, if 2 rows are the same, then you're going to end up with free variables. Okay, because according to our 3 legal actions, we can subtract our rows. So, because of that, we can have our determinant A equal to 0. And it works for columns too, because of property 2. Transpose it. Oh, now it's 2 columns that are same. 2 rows are the same. Still equals to 0, the determinant. Okay? And then 4 is technically the exact same thing as 3. It's just, our legal action says, one of our 3 legal actions says you can have a multiple. If a row is a multiple, you can divide it. You could divide that row with a non-zero, with any non-zero number, or multiply with any non-zero number. So that's why 4 works. Number 5, the determinant of AB, you can separate it into 2 products of determinants. And then the determinant of A, for the inverse of A, is just 1 over the determinant of A. Okay? I know, a big list of properties for determinants, but it's not as bad. You will get used to it. Okay? Alrighty, and that is about it. Alright, cool. Congrats, you've learned determinants. I know the most annoying part about determinants is just dealing with big matrices, especially when they do not have enough zeros. But that's okay. That's what computers are for. Alright, so cool. So yeah, hopefully that's very helpful and helps you kind of break down and understand how determinants works and where it came from. So yeah. So thank you guys so much for watching, and I'll see you guys in the next lecture. See ya!